Hello, my name is Anthony Velasquez, and I'm going to be presenting on the Moncrief Pedestrian Bridge Replacement Project. Now we're going to be using AASHTO Type 2 beams for the superstructure, and let's go ahead and start this presentation now. Now in this presentation we're going to talk about some of the project parameters like why we need to replace the bridge, the input parameters for the beam itself, the size, etc., stresses and stress limits that are going to be acting on the beam, deflection caused by loads and camber, flexural capacity of the beam and the ultimate design of it, and lastly, cracking moment so we can find the reinforcement limit. Now this is a bridge in Jacksonville, Florida on the northwest side on Moncrief. Now this bridge was actually hit by a truck a few years ago, and no one really noticed it until recently when the city was doing, I guess someone was driving around and called the city, and the city decided that, yeah, we need to replace this bridge. Not only that, but the vertical clearance on the bridge is really low. It's about 14 feet 4 inches when it should be at 17 feet 0 inches if it wants to be up to standards to today. So we need to raise the bridge and we need to make a new superstructure, completely new superstructure. And as you can see on this drawing here, we're going to have two AASHTO beams next to each other with the deck right in between. So people are walking here and some fence. Now we have a lot of input parameters, so I'm not going to go through them too much, but these input parameters are just beam dimensions, weights, concrete strength, all these kinds of parameters that you need to find in order to design the beam. Now the standards on the FOT website also give you guidance on how your pre-stressing steel should have, or the pattern of the pre-stressing steel on the beam. Now as you can see on this top right figure, these are the locations of the strands, and I have placed 7 strands on the first row and 4 strands on the second row. I use this, you do trial and error kind of, and you see how many strands you need, and I needed that many strands. Now these are all still parameters for pre-stressing, so eccentricity at the location of the centroid of the pre-stressing steel, section modulus. In the end, we're just trying to find what is the jacking force so that we can find stresses. Now, we also have to consider if there's the stresses at the end to see if there is any need to debond or harp the beams. Harp the steel, the pre-stressing steel, but it seems like we're good. We have 755 kips of end forces, and we have about 363 kips here. So we are okay on our debonding limits, and we don't need to do any of that. Next, we need to calculate the loads that are going to be acting on the beam. Now we have the self weight of the beam, the dead loads due to the concrete and the railing, etc. The live loads of the pedestrians, that's 90 psf. This is a typical live load for NLRFD. And we add them all up, and we have 588 kip foots for just service loads, but if you do ultimate, it goes up to 771 kip foots. Next, you want to find the stresses and the stress limits on the beam using the parameters we just found before. Now we have transfer and service. So a transfer is just the pre-stressing before losses and including the self-weight. So you can see some of these equations here. Find stresses at the top, stresses at the bottom, stresses at the end, and these are all just to find stresses and see if the limits are good. Now in transfer, most of our stresses are in compression, top and bottom beam, but at service, which includes losses and includes all the dead loads and live loads that we have compression at the top fiber of the beam and tension at the bottom, which is expected. Next, we have to make sure that these stresses are okay, or they're allowable, they pass the checks. And in our case, we go to the ACI code and we see the stress limits here, and we see that we are okay. We pass them for both transfer and for service. Next, we want to find deflections. Now, deflections have two different let's call it 2 different stages. We have the short-term stage and the long-term stage. For the short-term, you have just the initial pre-stressing before losses, and the self-weight of the beam acting. Those are the only things causing deflection. Now here, this is deflection due to camber, and here is the deflection due to the self-weight. You add them both up, and you get deflection immediately after pre-stress. You have to compare this number, which is almost it's 0.65 inches. You got to compare that number to the limit. Now the limit depends on the code, but in the code we use for LRFD, we have L over 360, which is 2 inches. So we're way below 2 inches. We're very good. The deflection limit is met at the short term. At the long term, it's a little bit more complex. You have to include losses, all the loads, dead and live, and you have to include creep. So you have to find the creep coefficient in order to find the pre-stressing due to the pre-stressing due to the pre-stressing force after losses. And once you find the creep coefficient, which depends on the amount of time and the concrete compressive strength, you get this number, which is the total deflection due to pre-stressing tendons. Then you find deflection due to dead load and live load using your basic deflection equations depending on the loading on your beam. Finally, you add them all up and you get a deflection due to a long-term deflection, which we have to be almost 1 inch. Remember, the limit was 2 inches here. So we're still well under 2 inches. We're getting closer, but we are good for long-term deflection. Next, let's find the capacity of our beam. Now, there's also a lot of factors that we have to find, such as the reinforcement ratio, beta factors. We have to do several checks to make sure they are all good to go. The pre-stressing flexural failure stress, we got to find that, equivalent stress blocks, etc. You find all these, you find all of them, and in the end you find your phi factor, make sure it's tension controlled, which in our case it is, in order to find your nominal flexural strength, which we got to be 954 kipfoots. And using the phi factor, you get 858 kipfoots for your design strength. So that is our capacity. We want to design to this. So we got to make sure that our ultimate loading, which we calculated before, is below this number, which, as you can see in this equation here, it is 771 is lower than 858, and we have about 11% of wiggle room there, which is pretty good. Lastly, we want to find the cracking moment in order to make sure we have the minimum tensile reinforcement ratio that we need. And as you can see here, we find the cracking moment using these equations, and we see that 20% of that cracking moment, which is 748, is less than the phi mn, which is the ultimate. 858 is greater than 748. So we're all satisfied. And that is all for the presentation. Thank you so much for watching, and I hope you enjoyed this.